Hello everyone. My name is Sanid Rawat, and I'm back with another video. In this video, I'm going to be explaining all the second internal solutions, which was basically an MCQ test. And let's go forward with the question paper. Firstly, we'll start off with the true and false. So, the first question we have on our screen is minimize the number of arithmetic operation whenever it is possible. So, this is true. There are several reasons why it is beneficial to minimize the number of arithmetic operations whenever it is possible. Firstly, is the efficiency. Whenever we perform arithmetic operation, it is computationally very expensive. I mean, it takes a real heavy toll on your system because of its complexity. And by minimizing the number of operations required, we can just improve the efficiency and reduce the processing time. Second thing is the accuracy. By each arithmetic operation, we increase a certain degree of error and due to which we can accumulate over multiple operations. By minimizing the number of operations, we reduce the overall error and improve the accuracy of the results. The third thing is the robustness. The arithmetic operation can also lead to numerical instability and divergence, especially when dealing with large or small values. And by minimizing the number of operations, we can reduce the risk of numerical instability and make the algorithm more robust. And the fourth thing is the memory usage. Each arithmetic operation requires some storage space in memory, and by minimizing the number of operations, we are also reducing the storage space which is required by the operations in the memory. And by minimizing the number of arithmetic operations, we can lead to a more efficient, accurate, robust, and a less memory usage system. Now let's move on to the second question. Uh, Avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference before doing the other operation. I would say this statement is true because when we take the difference of nearly two equal numbers, it can lead to a loss of accuracy and numerical instability, especially like when we deal with floating point arithmetic, because in the difference between two nearly equal numbers, uh, the loss can be very very little, due to which we can lose precision in floating point of arithmetic. For example, we have this value of a and we have this value of b. So as you can see, in really like the end part of the decimal, we have a difference of 0.0000001 if we reduce b minus a. In this case, the value of C is so minute and it may be lost due to the precision of floating point arithmetic, and this can lead to inaccurate results and numerical stability. Especially if C is used again and again in our calculations, this can really lead to a problem. So, if we can avoid taking such insignificant differences, then we should go for it, because it can again involve algebraic manipulation or reordering of calculations to reduce sensitivity to small changes in the input. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended that the difference before performing uh, these other calculation, it is recommended to take the difference before performing the other calculation. This can help to reduce the impact of the loss of precision and improve the accuracy of the results. Let's move on to the next question. So here we have that adding or subtracting numbers starting with the smallest number and works with number in ascending order. I would say that this statement is true because when we add or subtract numbers of different magnitude, it is very important to start with the smallest number to reduce the impact of the limited precision of floating point arithmetic. Because as we know, it's accurate till the fourth decimal place, and this is because small numbers have fewer digits and are less sensitive to rounding errors than large numbers. By working with the numbers in ascending order, we can also reduce the accumulation of rounding errors and numerical instability. This is because rounding errors can accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to these errors. For example, let's say we have these two numbers. A is 1.23, B is 0.04, C is 45.67, D is 0.0005. If we add these number in the descending order, we get 46.9035. But if we add them in ascending order, we again get the same result. But if we add this small number first, it reduces the impact of rounding errors and improves the accuracy of the results. So yeah, if we just start off with the small numbers, we can get some really accurate results, and it can be really helpful in some complicated calculations. Let's go on to the next question. Do not formulate an algorithm that tests whether a floating point number equals zero. So yeah, this statement is again true because it is definitely not recommended to formulate an algorithm that tests whether a floating point number is zero, because floating point numbers are not exact. I mean, they are not accurate, and their values are really rounded off because again we have limited access to, like, again, as I mentioned earlier, that we can just we usually take till the fourth decimal place, then we continue to the exponent part. So in most of the cases they are rounded off. That's why we shouldn't use it again and again. And due to the limited precision, it is really difficult to represent certain numbers exactly, including zero. This means that even if two floating point numbers are mathematically equal to zero, their representation in memory may be different due to the rounding errors. And instead of testing whether a floating point number equals zero, it is better to use a threshold or tolerance value to check that the absolute value of the number is sufficiently small. And this approach is known as the epsilon test. Here's an example of epsilon test of the pseudocode. You can read this. In this algorithm, x is the floating point number being tested, and epsilon is the tolerance value. The ABS function is the absolute value of x, and the function returns true if the absolute value is less than epsilon, indicating that it is effectively zero. In the epsilon test, we can handle floating point numbers more accurately and robustly than testing for exactly equal to zero. Okay, let's move to next question. Yeah. Conditioning of problems is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way to detect suspected ill conditioning is to alter the parameters by small amounts and observe their effect on the solution. I would say the statement is partially true, because ill conditioning of problems due to improper formulation can also be due to the nature of problem itself. Ill conditioning means that small changes in input or parameter of the problem can lead to large changes in output or solution. I mean, let's say if the nature of the problem is itself that the statement is ill computed, then how can we have an accurate solution? I mean, if the problem contains some error in itself, then it would be really hard to get to an accurate solution. And one way to detect suspected ill conditioning is indeed to alter the parameters by small amounts and observe their effect on the solution. This is known as sensitivity analysis. By analyzing the sensitivity of the solution to changes in the input parameter, we can determine whether the problem is well conditioned or whether the problem is ill conditioned. If the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. However, simply alternating the parameters by small amounts may not always be enough to eliminate ill conditioning. In some cases, a careful reformulation of the problem may be necessary to improve its condition. This may involve changing the formulation of the problem, introducing additional constraints or assumption, or using a different numerical uh, or algorithm. While detecting suspected ill conditioning through sensitive analysis is a useful first step, and addressing ill conditioning may require a more thorough analysis and reformulation of the problem. Let's continue to the sixth question. After a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error grow in each step of the calculation. In such case, reformulating the solution procedure to get a stable numerical algorithm. Again, this is a partially true statement. Numerical algorithms can indeed lead to numerical instability, where error grows in each step of the calculation. This can be due to a variety of factors, such as ill-conditioned problems, numerical round-off errors, or instability in the algorithm itself. And in order to ensure numerical stability, it is really careful to analyze. It is really important to carefully analyze the algorithm, its implementation, to identify potential sources of instability, and this may again involve the testing of algorithm on a range of input values, so that we can confirm that okay, this is our sample size, and we have tested within our samples, and examining the behavior of the algorithm as the input values are varied, and comparing the results with analytical or exact solutions wherever it is possible. If let's say we detect some numerical instability, then the solution procedure may need to be reformulated so that we can get a more stable numerical algorithm and our answers may be more accurate. We can do this by using alternative numerical methods or algorithms that are known to be more stable than the existing algorithm that we already have, to reduce the impact of numerical errors or round off, or introducing additional constraint or assumptions to improve the conditioning of the problem. While checking for numerical instability, it is also an important step in the development of numerical algorithm, and numerical instability may require a more thorough analysis and reformulation of the algorithm to ensure that it is really reliable for a range of input values and conditions. Let's go to the next question. If severe rounding errors and consequent loss of significant digits is anticipated, and if no alternate formulation to avoid this is possible, then carry more significant digits in the critical calculation using floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that of the other floating point quantity. Yeah, it's true. Severe rounding errors and consequent loss of significant digits can occur in numerical calculations, particularly while dealing with the quantities that vary widely in magnitude, or when performing operations on values that are close to the limit of the machine precision. And in such cases, no alternate formulation is possible. Then, ultimately, to avoid the loss of the precision, carrying more significant digits in critical calculation is the only solution that we are kind of left with to minimize the impact of rounding errors. And one way to achieve this is by using floating point numbers in double precision mode, which allows for twice the number of digits in the mantissa compared to standard floating point numbers. This can help to increase the precision of critical calculations and reduce the potential for rounding errors to affect the accuracy of the final rounding. And it is also important to note that increasing the precision of calculation can also increase the computational complexity and memory requirements of the algorithm. Therefore, it is important to carefully balance the need of computers uh, against the computational resources available, and to consider alternative methods of formulation so that we reduce the impact of rounding errors on the final result. Let's go ahead. Double precision requires large memory space and slows down calculation. Again, it's partially true. Double precision requires a more memory space than the standard single precision, as each double precision floating point requires 64 bits, which is typically 8 bytes of memory compared to the 32 bits for a single precision number. However, whether or not double precision slows down calculation depends on specifically the context and computation requirements of the algorithm. In some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. In these situations, the benefit of increased precision may outweigh the additional memory requirements and additional cost. In other cases of lower precision, it may be sufficient where the computational requirements are very, very limited, or it may be more efficient to using a single precision floating point numbers, or consider alternate formulation that reduces the impact of rounding errors on the final result. Overall, the choice of precision for a numerical algorithm should be based on careful consideration between accuracy, computational efficiency, memory requirements, and many other factors. After which we can decide our approach that how we have to go forward. Let's go to the next question. Yeah, in the third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. So yeah, I have performed some calculation here. I'll quickly run through it. Based on the given information, we can make a guess, assuming that formula used to find the square root of 5 is this. And here I have taken xn as the nth approximation, xn plus 1 is the n plus 1 approximation. We can estimate the value of x3 as the third iteration as follows. Then I have calculated these values with the help of this formula. I have the value of x naught, x1, x2. Now we can assume that the relative error is defined as I have mentioned the formula here. We can again calculate the relative error between x2 and x3. Then we can, if we solve it, then we'll get our relative error as 0.0013. Solving for x3 in the equation, we have this relative error, and then we can do these steps forward so as to get our complete result. And in the end, the third approximation of the square root of 5 using the Newton-Raphson method with a starting point of 7 and a relative error of 0.0013 is approximately this. Okay, let's move on to the last question. Mm, The iterative methods are compared on following parameters: rate of convergence, amount of computational effort per iteration, sensitivity of methods to the starting value, and immediate values. So, as we have mentioned in all the former questions, that while we are selecting our algorithm, while we are altering it, while we are looking for different solutions, there are various requirements in the system. Firstly, there are computational requirements. Secondly, the rate of convergence is also necessary. Thirdly, sensitivity of the methods is also necessary so that it doesn't take a toll on your system. I've also mentioned with a quick explanation of all these terms. A rate of convergence is basically how quickly the iterative methods converges to the desired solution. How quickly we can get to a solution. The faster the rate of convergence, the better the method. Amount of computational effort, it refers to the amount of computation, the amount of processing required to obtain the next approximation in the iterative process. A method that requires less computation, less processing is definitely the better one. Then sensitivity of the methods to the starting values and the immediate values. This refers to how the method is used to initially guess and immediate values used in the iterative process, which are less sensitive to the initial guess and intermediate. By here we are done with the first internal questions. In the previous video, I have explained the three questions which were a little bit detailed, and here the true and false part is complete. And in the next video, we shall cover the second internal question papers, which mainly includes multiple choice question. Thank you for watching.